Well, I know those combined gas law problems can be a little tough here, so I've got two example ones that I'm doing for you. Now, hopefully you learned kind of through the inquiry style and you practiced, and this is just to further deepen your understanding. So let's read these problems, let's annotate them, let's figure out what they're asking, plug in, do our algebra, and rock it. Alright, so a 2-liter balloon, so that's one thing I'm given, was stomped on during a hot summer day, 80 Celsius. The balloon was 80 Celsius? That's a ridiculously hot day. A hot day would be like 30 Celsius. 80 Celsius is like you die, because 100 is boiling. Who wrote this problem? Oh my gosh, this is like a hot day on Venus or something. The balloon was originally at 1 atm. When stomped, the volume was compressed to 0.5 liters. If the pressure exceeded 3 atm, the balloon will pop. Will the balloon pop? So basically, this isn't P2. We need to know P2, because we need to know if it goes above 3 atm. So we know V1 is 2 liters. We know T1 equals 80 Celsius. Again, that's ridiculous. Actually, we don't know T2, do we? But it doesn't say anything about the temperature changing. I'm going to assume that this is the same as T2. Not 100%, but I don't know what else to do. And then V2 is 0.5 liters. And what's P1? Did I skip it? Oh, P1, there we go. P1 equals 1 atm. So now we have P1 V1 over T1 equals P2 V2 over T2. But we're assuming temperature's constant. That gives us Boyle's law. Let's plug in. We have 1 atm times V1 is 2 liters equals P2. We don't know that. That's what we're looking for. And V2 is 0.5 liters. I can already tell, since the liters has gone down by a factor of 4, P2 is going to go up by a factor of 4. But let's solve it. So we need to get P2 by itself. So we're going to divide both sides by 0.5 liters. Those divide out. Liters cancels. We have 2 divided by 0.5. So I know 0.5 goes into 2 4 times. So I have 4 times 1. So 4 atm equals P2. Now, it said if it exceeded 3 atm, the balloon will pop. So now I can write my answer. I can say, yes, the balloon will pop because the pressure gets to 4 atm, comma, which is above 3 atm. And there we go. It pops. All right, let's look at the next one. Next example here. A piston is initially at 0.5 atm, 3 liters, 27 Celsius. Warning, warning, must convert. Add 273 to Kelvin. It's got to be proportional. They've got to have the same zero so that it's directly proportional. So that gives us 300 Kelvin. At least it's a nice number. What temperature would it need to be if the volume and pressure change to 1 atm and 1.5 liters respectively? Okay, so P1 is 0.5 atm. V1 is 3 liters. T1, I already converted it, is 300 Kelvin. And then P2, it said it changes to 1 atm, so it doubles. And then V1 gets cut in half. So it looks like we're going to have to use the combined gas law because we're looking for T2. So I'm going to write the combined gas law and then plug in. I feel like I'm less likely to make a mistake if I write the combined gas law first. So I start plugging in 0.5 atm times V1, 3 liters, over T1, 300 K, equals P2, 1 atm, times V2. Is that? Oh, no, that's V2. I wrote V1. I hope you caught that. So 1.5 liters over T2. Now I need to solve for T2. The problem is it's on the bottom. Easiest thing to do here is to get rid of fractions by cross multiplying. Okay, so I'm going to cross multiply. You only need to cross multiply when the variable you want is on the bottom, remember. if I were solving for P2, it would actually take more time to cross multiply. So don't just do it without thinking, okay? So I have 0.5 ATM now times 3 liters times T2 equals 1 ATM times 1.5 liters times 300 Kelvin. I've got to get T2 by itself, so I ask myself, what's in the way? Answer, all this other junk. So that cancels out. Got to do it on both sides, though. I think my handwriting's actually getting worse. Is that even possible? Maybe I'm getting like arthritis or something. Okay, liters cancels, ATM cancels. Let's see, 0.5 times 3. Isn't that 1.5? I think it is. Yeah, it's 1.5. So that cancels. Leaves us with T2 equals 300 Kelvin. What the heck? So basically, the temperature didn't change at all. Oh my gosh. Okay, so we can say the temperature would still be 300 Kelvin. Gotta capitalize that. Wow. I feel like we just did a whole bunch of work for so little reward. Time to go eat some ice cream. Peace out.